Section 5.1 deals with special segments of triangles. This section deals with the main question of how do you find the center of a triangle? Now there's not one correct answer to this question because there are actually multiple different types of centers of triangles, and we'll talk about 4 of them today. So the first type of special segments in triangles is called the angle bisector. Now the angle bisector of a triangle is a segment that bisects an angle of a triangle. So in your notes, draw out a big old triangle. I'll call mine ABC. You can call yours whatever you want. And I'll draw in one angle bisector, let's say from angle B. I'm going to construct it using my compass and straight edge. And if you'd rather, you can just kind of measure it out using your protractor. So I'm going to have angle bisectors from all 3 vertices of the triangle. So here I'm going to measure out. I see that angle is about 76 degrees. So I'll measure out half that instead of constructing. And so you see I've got these 3 angle bisectors. Now the intersection of all 3 angle bisectors is called the triangle's incenter. So here I have that labeled and a point on that point of intersection. A note about the incenter is the incenter is equidistant from all 3 sides of the triangle. In other words, if you were to, with a compass, put your point on the incenter and the pencil on as short a distance as you can get to the outside, you'd be able to inscribe a circle in that triangle using the incenter. The next special segments, they're called medians. So the median of a triangle connects the vertex to the midpoint of the opposite side. So once again, draw yourself out a triangle. I've called mine DEF. And first I'm going to construct the midpoint of segment EF. If you'll recall the midpoint construction, I've got my point on F, and the compass is open to a size greater than half the distance. And you can see kind of in light pencil there, I've got 2 intersection points. And that determines the midpoint. And then I'll just connect vertex to midpoint. If you do that to all 3 vertices, by the way, here I'm just measuring instead of constructing the distance, we have another point of concurrency. This intersection point is called the centroid. Whenever you have 3 medians of a triangle, their intersection is called the centroid, and that centroid is always 2/3 the length of the median. In other words, if you split up the median, the centroid splits it up into 2-to-1 ratio. So for example, if that length were 6 centimeters, then this would have to be 3 centimeters long. Total length is 9 centimeters. By the way, the centroid is also the balance point, or the triangle's center of gravity. If you wanted to balance this triangle on the edge of a pin, you would use the centroid as its balance point. Our third special segment is called the altitude of a triangle. Now the altitude is the segment from a vertex that's perpendicular to the opposite side. Now you could choose to construct this if you choose. I'm just going to measure it using my protractor. So for example, I've got this triangle, GEH, and I'm going to slide the 90-degree protractor. You can see the protractor is just slightly too small. I want it to reach all the way up to point H. So instead I found something else with a right angle on it. I've got this triangle, this kind of plastic triangle, and I see I can match up to point H perpendicular to GJ. So that's one altitude from H. I'll find the altitude from J and the altitude from G. The place where those altitudes intersect is called the orthocenter. A note about orthocenters: if you had a right triangle, then the two altitudes are actually on the sides of the triangle. And so the orthocenter is actually a vertex, provided you have a right triangle. If you have an obtuse triangle, then the altitudes are actually outside of the triangle. Here's an example. Here I have an obtuse triangle with one green altitude marked in. If I want another altitude, I actually have to extend one of the sides. And so that red altitude, even though it's not inside the circle, inside the triangle, it's still an altitude. Likewise, from the third vertex, I have these three altitudes. In order to find the orthocenter, I have to extend the altitudes. And so there is my orthocenter of that triangle. So that brings us to our fourth special segment, perpendicular bisectors. A perpendicular bisector is the segment that is both perpendicular and also bisects a side length of a triangle. So let's look at segment KL. Here I'm going to construct a perpendicular bisector, and that's done just by bisecting the segment. So I've got my two arcs, and if you connect, you get your perpendicular bisector. So I'll do the same for the other three sides. Find the midpoint and then go perpendicular from that point. And we see we have another point of concurrency. The intersection of perpendicular bisectors is called the circumcenter. Now the circumcenter is equidistant from all three vertices of the triangle. In other words, the distance from the circumcenter to point K, to point L, and to point M, all three of those side lengths are the same. Another way to picture that is if you had, let's say, a smaller triangle, so I can get my compass in there, the circumcenter could be the middle or the center of a circle that completely circumscribes a triangle. All right, to find the median from point E for this triangle, the first thing you want to do is graph the triangle. And then the median connects this point, point E, to the midpoint of the opposite side. So it's maybe somewhere around there. So we want to find the equation of that line. The first thing we need to do is find the midpoint of that point. Then we'll find the slope of that line. And then we'll plug that information into the point slope form. So first thing we want to do, we want to find the midpoint of the opposite side. Since we know it's going to be opposite of E, it has to be the midpoint of CD. So add up the x's, divide by 2. So that gives us 1 and -3. So we have guaranteed now that this point is 1, -3. Now we need to find the slope. So we need to find the slope of the midpoint and point E, so that line. So to find the slope, we'll use the difference of the y's, so -3 and 3. And then the difference of the x's, 1 and -2. So it's -6 over 3, which is -2. Then you're going to use that information and put it into the point slope form. So that information, I mean that slope, and then you can either use this point, or you can use point E. I think I'll use point E. So I know that has to go into the slope-intercept form, or sorry, point-slope form. And the slope that we're using is -2. And the point that we're going to use is, well, this point up here. We have -2 is the x value. So we could say +2. And then 3 as the y, so -3. Then to get that into slope-intercept form, we'll use the distributive property and then add 3 to both sides. So we can check our work. Y equals 2x minus 1. And we want to graph that. Y equals 2x minus 1. So the y-intercept is -1, and the slope is down 2 over 1. All right, so that is the equation of the median through point E. So, to find the equation of an altitude through point H, you know that it needs to go through this point, and it has to be perpendicular to that side. So we need to find the slope of the side first. So to find the slope, of FG, we want to use rise over run on these 2 points. So that's 6 over -2, and that gives you -3 for the slope. But we don't want to use that slope. We want to use the perpendicular slope. So the perpendicular slope, and so that would be just 1/3. Now we're going to use this slope and point H to make the equation of our line. So we'll use point slope form, and we'll plug in the slope. We know this has to be 1/3. And then the point, it has to go through H, which is 3 and 5. And then from there we can, using algebra, solve it into slope-intercept. Yeah, use the distributive property, and then add 5 to both sides. Gives you y is 1/3 x plus 4. And on your drawing, what that's going to look like is you know that it goes through 4, so there's your slope or your y-intercept, and then the slope is 1/3. So up 1 and over 3, and then we could also go back 1 and down 3. Sorry, back 3 and down 1, so that would look something kind of like that. All right, to find the perpendicular bisector of segment AB, we know we have to go through the midpoint of AB, so it's going to be, somewhere kind of around there, and it has to be perpendicular to that segment. So the first step will be to find the midpoint of that point, the midpoint of this segment, and then we'll find the slope of that segment as well, and then find the opposite reciprocal slope. So the midpoint of AB is 2, -1. So we know that this point has to be 2, -1. Next, we want to find the slope of AB. So the slope is -2/3. But we don't want that slope. We actually want the perpendicular slope. So if the slope was -2/3, the perpendicular slope is the opposite reciprocal. Now, we're going to use this point, that slope, and this point, and we're going to plug that information into the point slope form and solve for y, right? Put it into the slope-intercept form. And so if we subtract -1 from both sides, we're left with a final answer of y equals 3 over 2x minus 4. And then we could graph that just to sort of check our work. We know that the y-intercept is here at -4. And the slope is 3 over 2, so we go up 3 and then over 2. So it's actually kind of, is that right? Oh, I guess I drew that pretty poorly. Wait a minute. This isn't -4. This is -4. Okay, so the line should actually be right there. Hey, that looks a little nicer. So y equals -4. Oh boy. Y equals 3 over 2 x minus 4.